Okay. Can everyone hear me at the back all right? Excellent. So thank you so much for coming to my talk this afternoon, which is implementing a JVM in Java and Rust. And I want to thank the DevOps organisers for having me come on stage to Loser by Beck, which is absolutely a lifetime goal there. Every technologist wants to have that as their opening song. Okay, so fundamentally, we're going to be talking about the Rust part of the implementation here. So it's probably a good thing to do right at the start is to find out what people's background is and see if I can kind of get a level as to where to pitch some of this stuff. So hands up if you have programmed in Rust at all. Hands up. Okay, about a quarter to maybe a fifth of you. Okay, that's about what I was thinking. Hands up again if you're programming professionally in Rust, i.e. you're actually deploying production code in Rust. No hands. Okay, good. That's about what I thought. So that's good to know that my material is probably pitched, about right somewhere. So for those of you who haven't met me before, I'm Ben Evans. I'm currently principal engineer at New Relic. I am thoroughly branded. I even brought a pair of New Relic socks with me, although I didn't wear them today. Prior to being at New Relic, I was one of the co-founders of jClarity, which was sold to Microsoft earlier this year. And before that, I've done a bunch of stuff, mostly in banks and financial companies. So I was at Deutsche Bank and before that at Morgan Stanley. If you want to know what happened with the Google IPO and where the bodies are buried about that particular story, then buy me some beer later and I might share. I'm also known for a bunch of my work in the community. So I'm a Java champion, which is Oracle's kind of community lifetime achievement award in the Java space. I've won the Java Rockstar Speaker Award a bunch of times. And for 6 years, I served on the Java Community Process Executive Committee, which is sounds really impressive, but actually was a lot of meeting rooms and a lot of committee decisions. So not actually all that fun to most developers. And although I live in Barcelona now, where I work at New Relic, I spent a lot of time helping to organise the London Java community. And it was actually almost exactly 10 years to the day that I came to my first DevOps, which was actually my first Java technical conference. So it's been something of a long, strange trip. Okay, so let's move on and actually meet the Rust implementation and talk about why I decided to do any of this in the first place. I should say at this point that what I'm presenting here is purely my own open source project. This was just something I did for fun. It's not an officially sanctioned New Relic project at all. So much so that I don't even have to have a safe harbor slide, which for those of you who work for large publicly traded corporations will know is the bane of your speaker existence. So what were my goals in really deciding to implement this JVM? Well, it was supposed to be exploration. It was supposed to be teachability. Before I was at New Relic, I used to spend a lot of time teaching Java, especially the deep internal stuff, and just introducing it to an audience of Java developers who probably haven't thought too deeply about how the internals of a VM actually works. For lots of reasons, Hotspot is not actually a great machine for teaching people. It's a fantastic production-grade machine for actually running your code, but for actually understanding what the hell is going on when you type Java hello world at the command prompt. Hotspot is not a great place to start. So I wanted something which was teachable, and I thought about creating a kind of cut-down virtual machine that wasn't really Java, and then I thought, well, that's no fun. So instead, we would actually try to make a VM that was actually capable of running real Java programs and real Java class files. And spoiler for the end of the talk, I have. It doesn't do everything, but it does do some stuff, and within a few, limited boundaries, it will actually run real programs. Okay, great. So then I thought, well, how am I going to implement this? What languages could I use? Well, if I'm teaching Java developers, then an obvious choice of implementation language would be, hey, what about Java? And I do actually have an implementation of some of this in Java, but I'm not going to talk about it all that much today. It turns out that actually trying to implement a Java virtual machine in Java, apart from the circularity and the brain-meltingness of it, it turns out that Java is not actually an especially good implementation language for that. And you end up doing some pretty horrible, dirty hacks in order to get it to work at all. So I'd done a certain amount of work with it, but I was never really satisfied with it. And then I just suddenly thought, well, what about an opportunity to teach myself Rust? And again, for the few people in the room who have actually written Rust code, I would appreciate it if you wouldn't heckle my code too much, as this is actually the first substantial program I've ever written in Rust. Apart from a few Hello World things, this was the first thing I decided to implement. I don't know what that says about me. Probably, I should go and see a psychiatrist. I probably think they probably have something to say about that as to picking a VM as your first project. But that's what I decided to go for. The Java version, by the way, is available. So if you actually do want to play with the Java implementation of this, which predates the one I'm going to talk about today, then by all means, please go and have a play with it. All the code's up on GitHub, and we will as we will see. So okay, so we're going to think about implementing a VM. So what are we going to do? Well, I suppose it kind of helps if we have a map of what we're looking at. What is actually inside a modern VM? I think some of you who've been to see me speak before may well have seen this slide. This basically represents, I think, 3 of the 4 major subsystems that a JVM has. You see, on this side of the line here, we have class file creation. So that's basically where the typical Java developer lives and works. You write Java source code, it's fed through Javac, which is the source code compiler, and it produces a class file. Okay, that's the kind of the part that developers normally think about. What we're interested, though, is what happens after that. What happens when we take a class file that's been compiled and is sat there on disk? How do we take that from just being a frozen, dead thing and turn it into something that will actually run, something actually which is going to be executable code? Now, the path here is pretty straightforward. You take the class file, which is bytecode. It's not anything really like machine code, as we'll see. And all Java programs go through a class loader. So you have to check the class file, make sure it makes sense, make sure it's well formatted and doesn't contain any evil surprises in the bytecode. And if all of that is well, then it gets loaded into the VM and is then available to execute. In Hotspot, the methods go into a thing called the method cache, which basically is just a place where we've dumped the bytecodes that correspond to the individual methods. And one by one, they're fed into the Java interpreter. And then from there, providing a method is sufficiently hot, it will end up being JIT compiled. And some separate private VM threads will have a look at the execution parts of the code and will optimize it. And from that, will produce optimized machine code, which will then be placed into this area, the code cache, which will ultimately replace the bytecode level copy of the same method. There's obviously much more to it than that. There are things like inlining, which can collapse multiple methods, but that's the basic idea. Okay, so far so good. Now, obviously, the one major piece of the JVM that we haven't talked about here, which is missing from this diagram, is, of course, garbage collection. There's not really a representation of the heap as a runtime data structure here. But we all know that secretly, as well as this diagram, there's also the hidden garbage collection system as well. So what are we going to implement? Well, what we won't be implementing is a JIT compiler, because those things are damn hard to write, and we have enough to do just to implement an interpreter and a class loader. And the truth is also garbage collection turns out to be an incredibly difficult thing to do in Rust. So I also punted on that. So I figured that if Alexi can get away with shipping Epsilon, a garbage collector that doesn't do any garbage collection, then it's fine for my toy project as well. So we don't do any GC either. Okay. It turns out that with a class loader and an interpreter, we kind of have enough to do. So let's take that as our baseline. Class loading, interpreter, something that pretends to be a garbage collector but really isn't, and that's kind of enough to be going on with. Okay, so let's just do a few basics. Hands up if you are familiar with the basics of how a Java bytecode interpreter works. Okay. Okay, that's cool. A few more people than I was expecting. So I'll go relatively quickly over this, just so that we get a bit more time for the demos. So we need to talk about 2 things. We just need to talk about some basic grounding for those folks who haven't seen inside an interpreter before. And then we kind of need to move on and think about the available areas of memory that a JVM has at runtime. So just as every Unix process has runtime data structures that it needs, a stack and a heap and so forth, so Java programs, which are, of course, also executing Unix processes, have not only the operating system level runtime data structures, but we have our own internal structures which are particular or peculiar, you could say, to Java programs. So we'll need to talk about some of those as well. Okay, so the interpreter is the initial code execution environment, and in our case, it's the only code execution environment because no jet compiler. It's stack-based. Now, hands up if you know what it means when I say the JVM interpreter is stack-based. Okay, about half the room. For everybody else, what I don't mean is that it has a call stack. Yes, it does have that, but it's not the only stack it has. All programming languages, C++, Python, Ruby, Java, whatever you like, we have the idea of one function or one method calls another one. And so you can build up a stack, and then if something terrible happens, you get a stack trace of everything that previously called you. That idea of structured programming goes back decades and decades and decades. So yes, absolutely, the JVM interpreter has that idea as well. But in addition, we have an internal private area for evaluating temporary values that we want to use in our computation. And that temporary evaluation area is private to a method and is implemented as a stack. Now, on real computers, we use registers for those temporary values when we're actually computing them. But the JVM doesn't have any registers, so we need an alternative data structure, and so the evaluation stack is the key part that we have there. This is just one of the many, many ways in which the JVM's bytecode is not really machine code at all. Some of you who may have learnt Java back in the dim and distant past when dinosaurs walked the earth might have heard the claim that a JVM is machine code. The bytecode is machine code for an imaginary CPU. Hands up if you heard that description of bytecode. Yeah, it's wrong. Wrong, 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 wrong. It's really nothing like that. Sure, it's binary, but it doesn't look anything like the machine code of real CPUs. I would say it's halfway between readable source and machine code. If you held a gun to my head, I would say that despite being written in a binary format, it's actually closer to source code than it is to machine code. If you're a compiler theory geek, then you probably are familiar with terms like an intermediate representation or an IR. You're probably also familiar with terms like front half and back half of a compiler. Well, in that case, Javac is not a full compiler, but merely the front half of a compiler. So I can see a few people nodding, so those terms, I hope, make some sense. So what that means is that some of our high-level features are compiled away, and they don't appear in bytecode. For example, things like for and while, etc. are gone. They're just branch instructions. There's only if instructions and jump instructions left. That's all we have. Those language features have been boiled away. Other things, such as inner classes and checked exceptions, are all fictions of the language level. They don't exist in the bytecode. They're just gone. So the Java source code compiler does do some things to boil away language level features, but ultimately the bytecode that it produces, the bytecode that is produced for Java is very, very close to the source language. I need to be careful here because in some other languages, notably Scala, the bytecode that's produced by the source code compiler looks nothing like the original language. So in Java's case, we stay very close to the source representation. Other languages, not so much. The other reason that bytecode is not similar to machine code is because it's a weird mixture. It's a weird mixture of really low-level things like take this int and add it to this other int. Well, that's pretty much the most basic thing that you can ask a computer to do, right? Versus on this object, go and find its corresponding method virtual function pointer table, determine whether an acceptable function exists, and call it no matter where it is in the class hierarchy. Now that doesn't particularly sound like a low-level operation that a physical machine would do, right? And spoiler, it's not. So you have this odd mixture in bytecode of things which are high-level and things which are low-level. So that's, I guess, the other thing to say about why it's not really the same as machine code. Okay, so one other thing really important. JVM interpreters require class files. There is no other way to execute code on a JVM other than creating a class file, passing it through the class loader, and starting to execute it. No ifs, no buts, no maybes, no backdoors, no other way of doing it. make a class, turn it into a byte stream, feed it into a class loader, execute it. Always and without exception, that is the way it's done. Okay, so once we've done that, what does our interpreter look like? What's our simplest representation? Well, it's a switch statement inside a while loop, basically. That's what it is. You have a method called, well, I've called it here, just for the sake of argument, exec method, which takes an array of bytes. And inside that method, we have a switch statement. Each case of the switch will dispatch one opcode, one instruction in that bytecode file. And then each time we do a method call, so suppose we call a static method or we do an instance method, maybe a virtual call, then that will, in the stack of our interpreter process, which is what's executing our code, that will place another copy of exec method. So if you looked at the C++ style stack trace of our interpreter, assuming we were implementing in C++, you would see a whole bunch of calls to exec method. And each one of those would correspond to each Java method that we'd called. So here's how it would look. I suppose I could actually have included an invoke opcode so you could see it calling exec method again. But basically, we're going to do something like this. We've got a set of local variables which we need to pass in so that we can have somewhere to hold the function parameters that we're passing into the method. We're going to create our new interpreter evaluation stack, which, just as I promised you, is private to this method. We've got a loop counter, and now we just step through. We look up our instruction, we turn it into an opcode, and then we switch through that and find the different cases of the different operation codes that we have. Okay. Hands up if you've seen a representation of an interpreter, not necessarily a Java one, maybe a simpler one, that looks a bit like this before. Okay, good. By the way, as I'm here, if you're actually talking about real interpreters and real implementations, Hotspot does something much smarter than this. Hotspot's code does not look anything like what I just showed on the previous slide. It's all done with dynamic code and dispatch and smart table building at startup. But that's kind of just an aside. Okay. So far, so good. So what should we do? Well, we need to model some local variables. First of all, for the local variables that are contained inside each method that we're going to execute, and also to handle parameters coming into the method. We need an evaluation stack, because remember, there are no registers here. And if there are no registers, we need to calculate temporaries somehow. And if you can think of another way of calculating temporaries other than using registers or a stack, then come and talk to me afterwards. We also need what's called a constant pool. Now, a constant pool contains, well, you can probably think of some simple examples. Any literal string that you write into a Java source file. Any literal value that you assign a field to, well, in most cases, will get turned into a constant. So those are the kind of trivial examples. But one of the weird things about bytecode, and one of the things that I don't have time to go into in enough detail, is that the changes in the VM's bytecode over recent versions, a lot of it has been to do with adding new and slightly strange variations of things in the constant pool. Okay, I'm not going to explain that statement anymore, but it is true that the way that the bytecode shape has changed has got a lot to do with more and more things in the constant pool. And then finally, of course, we have our Java heap, which is global, it's shared, every call frame, every method, every thread can see the heap. Okay, so let's build a first implementation. We're going to need some integer arithmetic and returns, because we're going to do this in a TDD style. So we need to actually manipulate some data, and then our methods have to be able to return something so that we can actually test and see whether the interpreter ran the method properly. And we might need a bit of stack manipulation as well. Okay. So we're going to have the values, the local variables, and some test cases for TDD. We're going to do this in Rust, so it's probably time to say a few things about Rust. We're going to replicate some very simple functionality of my original Java implementation. We want cleaner class parsing. We want to use a convenient type system and a modern one. Potentially, we're also going to want to use lower level memory handling. And Rust is kind of famous for its memory safety. So that seems like a good thing to try to take advantage of as well. For people that haven't written in Rust before, I'm going to do a few slides of very, very quick Rust code. If you download a Rust project from GitHub for the first time, the first thing that you will probably run into is it has a very rigid project structure. You know, you might think that Maven is pedantic about source main Java. Well, Rust has very, very strict rules about where code gets placed. If you break the rules, it will give you very annoyed-sounding error messages and not tell you why. So my advice is to really learn to lay out some simple Rust projects first of all, and then try to figure out what the rules are. I mean, they're quite simple once you've figured out how not to break them. But they are pedantic. Lots of things in Rust are pedantic. And if you get them wrong, you will have a bad time. I haven't found any good way to make Rust override its rules and do things the way I wanted it to. Oh well. The environment setup is really simple. It has a tooling thing called Cargo, which basically is an extensible tool building platform. It's kind of like your Maven or your Gradle. It's quite nice. It's very fast. And connected to this, we also have a packaging system which Rust calls crates, which again is a pretty simple system. There's a single top-level file which declares dependencies for use with Cargo, and it's there that you will add in additional top-level dependencies that your project directly depends upon. The language is statically typed and strictly typed. It's very heavily type-inferred compared to Java. It has a lot of low-level types, including unsigned integer types, which is good, because we're going to be fiddling with bits and shuffling bytes around. And generally, dealing with shuffling bytes around in Java is bad, because all the integer types are signed. And if you've ever had to remember to mask off things using masks to correct signing bits and so forth in Java, you'll know what a pain this is. So having unsigned types directly there is also nice. Rust variables are immutable by default. So if you want mutability, you must declare it, and the types are very, very strict. For example, if you want something which is the size of an index to an array, what Rust calls a usize, it had damn well better be usize. You give it U16 or U32, and the compiler is going to tell you that that's not okay. And it will be a compile time error. So you have to fix things, and you have to deal with the types of things exactly the way that Rust wants you to. Rust uses the struct as its basic user-defined type. This isn't like in Java where you have a class and all the primitives live inline, but then you also have pointers and references to other fields of reference type. In Rust, you can do low-level memory layout just the way you want to, which can be really nice. It doesn't have a concept of a class. Structs have a declaration, which is about what their storage and their layout looks like, and it has an implementation which carries the methods effectively on the struct. It has very basic public-private access control. If you stick the word pub on something, it's public. If not, it's private. And outside this compilation unit, it's invisible. It doesn't really have OO. Rust is not precisely what I would think of as an OO language. Instead, well, for many reasons, it has no inheritance hierarchy to speak of. So unlike in Java, where everything sooner or later, every reference type ends up extending from object, doesn't work like that in Rust. You just have some stuff. You have a struct declaration which declares some storage, and then on top of it you can then say, well, and also here is a declaration of its implementation, and these are the methods it defines. You can use these things called traits. Hands up if you know what a trait is. Yeah. For anyone else who doesn't know what a trait is, just read that and think Java interface. Right? I'm glossing over a whole bunch here of things here, so people that know what traits are know how badly I'm lying at this point. But if you're coming from a Java background, just think trait equals interface. Okay, what else have we got? Language features. So we also have non-erase generics. You find a lot of use of Rust's option type. There aren't really nulls in Rust, which I think is a good thing. But the way that we typically get around it in the code is to use option a lot more than people coming from other languages, notably Java, would tend to do. We also have, and these are features which aren't really in Java yet, but they are definitely coming. There's a lot of use of algebraic data types. Hands up if you know what an algebraic data type is. Okay, so an algebraic data type, for people that don't know, is two things. Firstly, it means a tuple, and Rust basically supports tuples completely natively. And it also needs what you call a union type, which is also sometimes called a sum type. And in object-oriented terms, that's the relationship A is a B or C. so that any instance of type A is guaranteed to be either an instance of type B or of type C, and can be of no other type. Java, by the way, is getting both of these. It's getting an equivalent of tuples in the form of records, which are coming soon, and it's getting it's a vaguely equivalent concept to union types called a sealed type, both of which will be arriving, I would guess, probably in Java 15. So this is a huge thing, and the reason why we want it all is this bottom thing down here called pattern matching. And when I say pattern matching, I don't mean regular expressions. Pattern matching is a concept from other functional languages such as Haskell or Scala, and it's present in Rust hugely as well. Okay, what else do I want to say? Oh, one thing which is particularly annoying to Java programmers is that in Rust, these union types, they're called enums in Rust. Now, this is one of the things that threw me most about the language when I was first getting to grips with it. It took me ages to figure out that when they said an enum, what they actually meant was an algebraic data type. For those of you who are sure about the distinction, enums are about finitely many instances of a single type. Union types are about finitely many types. Effectively, you can think of it as the enum pattern lifted to type level. Okay, so unlike most people, I have kind of turned my introduction to Rust on its head. The main language feature that most people talk about to start with is storage and borrowing, and I've left that till last. And I think there is a method in my madness here. Rust is extremely pedantic about handling of storage, much more so than in Java. It gives you much more low-level control. So on the one hand, it tries to give you control, but it also wants to do it in a safe manner, which is quite hard to do. Basically, almost every bug in C++ boils down to either unsafe handling of storage or misunderstood assignment semantics. And Rust tries to deal with both of those problems at once. For example, it requires you to declare variables mutable if they need to be, otherwise it assumes they are not. It has no real nullability to speak of. It has both parse and refute by value or reference. And in Rust's case, only provably safe programs will compile. So in general, Rust will rather fail your compilation than allow something that it cannot prove is safe to compile. So that's quite a big statement. And in fact, there are examples of perfectly safe Rust programs that a human being can see will not lead to any runtime errors that the compiler will reject. It's a side effect of some theorems in compilation. Okay, and then this last point. Hands up if you've programmed in C++. Okay, good. So if I say Rust for non-trivial types defaults to move semantics. Yeah, so all of Rust's types behave like C++ R value references, except for trivial things like integers. Ints, I should say. Yeah, so that means that after you've assigned, if you have a line A equals B, and unless they are these degenerate copy types, if you then use B again, it's a compilation error. Because the value, the correctness part of B was moved into A, and B is now no longer really even defined properly. Okay? And that's I think, at the heart of the Rust borrowing model, which is one of the things that renders it so different from most other programming languages. Okay. That's been a lot of theory, so let's actually meet some Rust code. And for this, I will have to switch to Mirror. Drink some water real quick. Come on, where are you? How's the font size at the back? Bigger? Bigger, okay. How's that? Is that better? Yep, good, from the back row. Okay, so here's our first piece of Rust code. And I did promise it was going to be TDD. So what do we have here? Well, first of all, this syntax here with the hash mark and square brackets, you can probably guess what that is. That's annotation syntax. But in Rust, there is a kind of a blurring of the boundary between annotations and a general macro system. And Rust's macros are well out of scope for this talk. But the two things actually marry together in what I think is quite a nice way. Okay, so Rust has the keyword fn for a function. It uses snake case for its method names and for lots of its other names as well. And this one basically sets up a simple method to add things to 2. So what are we going to do? Well, we're going to create a vector, or a vec in Rust, and it has these 4 things here. And you can see that they've come in from a namespace called opcode, which fortunately enough, I have a copy of here. So these are actual genuine Java bytecodes. These are the numeric values for each Java bytecode in the set. Now, on this branch, this is a very, very simple version of the interpreter. We don't really do much. We basically only have a very few opcodes implemented. But if we come back here, you can see that the 4 we're dealing with here, well, 3 we're dealing with here, are iConst, iadd, and return. So I hope it's pretty clear what this code does when we're going to execute it. You load the constant 1, which is an int, because it starts prefixed with an I. Load int 1 onto the stack, load int 1 onto the stack, add them together, return the value that results on the top of the stack. Okay? So down here, sure enough from TDD, we're going to wire this up so we're going to get a 2 back. Okay? Pretty self-explanatory, I would hope. Now what we have to do, we've got the bytecode up here, and we've got a method here. So all we have to do is actually execute the damn thing. So how do we do that? Well, let's scroll up here. This one is a little more complicated. So this is a private function because it doesn't have a pub here. And it takes in a vector. Notice the angle brackets. Angle brackets means generics. Oh yeah, Rust generics are completely not type arrays or anything like that. So you can totally have generic types over any type you like, including a vector of unsigned int of size 8, or bytes, as we like to call them. And what happens? Well, we're going to take in this vector of bytes, and we're going to return a JVM value. Now, what the type JVM value, of course, we haven't defined yet, but hopefully the name is pretty self-explanatory. We're also going to set up one of these things, in a local variable table, or interp local vars. This basically is to allow us to pass values into the method should we wish to later. And then we're going to call this function exec method 2 with some string, our bytes, and our local variable table. What comes back, and I've named it, probably a little verbosely here, opt_rec. Now you can probably guess from the form of the rest of the code why it's called opt_. Yeah, it's an option. So either what will come back will contain some value, or it won't. If it does, then we should look at that value and return it. However, if it comes back as none, well, we're not actually going to throw an exception here. We're actually just going to pass back a reference which contains the null object. Okay, there's a bit of magic there. But the point here is that this match keyword is Rust's pattern matching. If you've seen this in other languages, hands up if you've seen a pattern match in Scala or Kotlin or another language like that. Okay, most people have. So yeah, this is just Rust's way of doing the pattern matching. Notice I don't need an explicit return statement, because in both cases, Rust is able to exhaustively follow the branches of the match expression and deduce that whatever comes out of here is either a value, which will be of type JVM value, or it will be this type JVM value of OptRec, which I haven't explained what that is yet, but I will do in a sec. So either way, this branch, these branches are exhaustive, and both of them produce a value of type JVM value. So therefore, Rust is able to infer that actually the typing here is all correct. So this is a slightly more advanced form of type inference than we might have seen. Okay, so far so good. So now let's have a look at exec method 2. This is in another file. And notice how we actually have to use these terms opcode, pubmod opcode to bring in that namespace into this file as well. So that's just basically like an import statement, but Rust is fussy about those, and you basically, this is where laying the project out carefully to follow the conventions becomes important. Okay, and so here is our declaration. We need a name for the class, we need our instructions, and we need our local variable tables, and it returns option of JVM value, just like we expected because we saw the none and the sum in the return type matching that we did earlier. So, okay. We set things up, we loop, because Rust doesn't really have fors or other types of looping quite the same way. The infinite loop construct here that we want to use is a loop. We get, based on our current position, which starts off being 0, and notice I declared it mutable because it's going to be our counter to move through the program again. And we're going to get the current value. Now notice that this has to go into a match expression, because lookup into a vector in Rust is not guaranteed to return a value. Dynamically sized vectors in Rust are a little bit tricky to handle. Things which have a statically known size at compile time are easy, because Rust can statically check the bounds types. But here, we actually have to handle this by taking it as an option. Okay, so having done this, we then advance by one piece. Rust doesn't have increment operators. Instead, you do a plus equals or an equals current plus 1, which I actually think is a good thing. It makes the code easier to read. And then our switch statement, as was in our Java code earlier, has turned into another match expression. So we match the opcode value that we're looking for. So here's iconst1, which says just eval, which, if you remember, was our evaluation stack that we set up. Rust is not object-orientated, so it doesn't really have constructors either. So what I'm doing here is I have something which looks like a static factory, which basically plays the role of the constructor for us. So that's our evaluation stack. We're just going to call iconst1 on it a couple of times. Then iadd will also delegate to that. And finally, iReturn will break out of the infinite interpreter loop that we're currently in, and it will return a sum of the value we popped off the stack, because this, of course, was being wrapped in an optional. Okay, so far so good. So now, here are some of the runtime structures we're going to need. We have this thing called an enum. Now, don't get confused. This is not an enum as we know it in Java. The possibilities for the enum are not instances. They are types. And in fact, notice that each type has different storage, different fields associated with it. So, for example, the Boolean JVM value has a bool inside it. The double has an F64, a signed floating point value of 64 bits. So these are algebraic data types or union types, if you like. Okay, and down here, notice that this is our enum. We also have an implementation for it, which does some crazy things. We always have to declare, for anything which we would use like an instance method in Rust, we would have to declare it using @self or @mute_self if you're intending to modify the struct. So basically, it's like having to write whatever the type is, this, at the start of each of your Java instance methods. You always explicitly declare it in Rust like this. So we can do a self match basically to produce the name of each of these types. So, for example, you probably know that Boolean in Java is represented by a Z, int is represented by an I, long is represented by J, and so on. Here is the trait-based things that I was talking about. So implement format : display. Yeah, this is kind of like toString. Because remember, there's no top type, there's no object, there's no natural set of methods that all of your types will get implementations for by default. So we have to provide them, including something as simple as, yes, I want to be able to display this. So this basically is an implementation of toString. Okay. And further on down, oh yeah, notice that Rust doesn't care what you call the files. You can stick whatever types you like in whatever files you like, and as many as you like. So in this case, this is just the runtime component, and we now have the interpreter eval stack. So as promised, this one just returns new instances and behaves like a static factory. iconst just takes its internal stack and pushes onto it. And you'll notice that it was defined as a vector up here. So iconst, and then I add, and you will see that the I've got this comment for a runtime checking interpreter. Type checks would go there. We're playing it fast and loose. If you put in an iAdd, an iconst and a dconst for a double constant, and try to add them as ints, things will probably break. But this simply deals with the fast happy path for ease of understanding. So we just match both of these to make sure that they're of the right type, int and int, and then we just add them together, wrap that into a JVM value instance, and push that back onto the stack. Okay, so far so good. We have got ourselves a little interpreter, and just to prove to you that it works, yep. And that was the test cycle. That's just how fast it is. The Rust compiler is really, really quick. And so you see I've done a whole bunch of different test names up here. Okay, only about 10 minutes left, so I shall just come back to my slides. First demo. So we need to pass class files as well, and instead I'm just going to come to the full demo and show you what else has been implemented. I'll skip that section. So. This is the great thing about having a pre-prepared project. I can just do git. Okay. Now you can see I've implemented rather a few more opcodes on the main branch than we have in the minimal interpreter. So now we have things like a bunch of support for doubles as well as ints. We've got fields, which go getting instance fields and static fields. We've got branching, ifs and gotos. And we've also got method calling. So I can actually now call from one method into another method, and it will call back into the interpreter. What else have we got? So okay, so far so good. And now we actually have not only the simple bytecode that we use to execute things as well, but we also have a helper method which will actually parse a class file. Because further on down from our little bytecode tests, we actually get to the point where we actually can load and invoke classes. So in this case, we set up our repo, which is where our classes are going to live. We create and parse a class based on it living inside a test resources directory. And then from there, we can pull a method out of the class repo, which has a method on it, and then just exec it directly. And so we now have class repo, method, and local vars, and once again it gives back JVM value. And inside here you can also notice that it says is native. Yeah, because I've actually implemented native method support as well. So one of my test cases is actually to call system current time millis and show that back and show that we can actually call down into native code from here as well. What else should I show? So let's look at the FieldHaver test. So this takes in a class called FieldHaver. And let me show you how. So this is the code we're going to execute. And what does it do? Well, it spins up a class. It's got a public field on it called I. We spin up an instance of FieldHaver, and we execute the put field instruction to store a value on it, and a get field instruction to get it back, basically to show that you can put something into the, effectively call a setter method, then call a getter method, and get the same value back. But this shows you that the object construction subsystem is working now as well. So let's just do a cargo clean. Yeah. If you do a cargo clean, then it will actually, unfortunately, typically want to recheck and rebuild the entirety of your dependency tree, which is, a little annoying, but compared to some of the things which will happen in Maven, it's not that bad. And it complains about a lot of my choices of names, because things like this, for example, Java lang system current time millis, that's designed to fit in with the JNI convention. So that's the same sort of name that you would expect for those functions there. And of course, Rust hates that. But even so, the actual compile cycle there was pretty quick, and so is the test cycle. Rust's test implementer has a really odd thing that it tests in parallel by default. So if you have any concurrency bugs in your code and writing a JVM, you kind of need to write concurrent structures a lot. You find them straight away, because what happens is your test suite stops working because two of your tests are suddenly fighting with each other literally simultaneously. Okay, so let's see how we actually parse a class. So by this stage, I've actually broken down it into separate crates, as they're called. And this font's a bit small, but these are the types of runtime data structures that we need to model. We need to have a structure which I've called OT class, and OT class is the runtime representation of a class. OT method, which is the runtime representation of a method, and so forth. So let's see the class parser. So at top level, we build a class parser with a stream of bytes that we've read from disk or somewhere else. And then from it, we parse by running these methods. We parse the header, we parse the constant pool, the type information, the fields and the methods. Attribute parsing doesn't fully work yet. But we do things like we check for the infamous magic number, Cafe Babe, that all Java class files have. What else do we have here? We parse the constant pool. So this is all the entries which are present in the class file, which are constants, such as strings and integers and floats and doubles and longs and all of that kind of thing. We also have things like class entries, which correspond to JVM class objects as well. Okay, and then if all of this parses correctly, then you will end up with a structure called an OT class. Which looks like this. And this thing is now the sort of the repository of the fields and the methods and the other metadata about this type that we need to construct new objects and to actually execute methods on it. We also need a runtime data store. So this one has the JVM values that we've seen already. It has the interpreter stack, and it also has the shared class repo. This is where we put all the classes that we load into, and we use this thing called a ref cell. And a ref cell is how we get around the problem of not wanting to make much data in our program mutable. Rust always wants things to be as immutable as possible, but sometimes that's just not possible. So there are several different language level mechanisms, cells, ref cells, arcs, which are used to kind of hide some of the mutability away. So for example, in this case, when I load a class, I need to modify a hash map and put some stuff into it, which corresponds to the new class that I've just loaded. And that's handled by a ref cell here. So in the class repo, I've only got a couple of minutes left. I'll also show you very briefly the main part of the interpreter. So this is the entry point. If I give this a class name, it will actually run a class file. So what do? We set up a repo, which is where our classes are going to live, and then we bootstrap it. Now, I pass into it this thing, which is a function pointer. And I pass into it the function pointer of the interpreter main loop. The reason I do that is because when I load a class, I'm going to have to call its static initializer, i.e. its CL init method. And I'm going to need to do that before the class is fully initialized. So the repo needs to actually call back into the interpreter to run some bytecode. getting that fixed was probably my biggest headache of the last month of actually getting Ocelot to work properly. Having done the Bootstrap, I then read my class file off disk, I parse it, add it to the class, and then finally, down here I actually exec the method. So it does actually have a complete line through, and it will actually execute class files. Not only that, but if we look at the Bootstrap method, which gets passed in a self object, a callback, and notice what the callback takes. It's a function type. So yeah, Rust has first-class function types as well. So in that method, in that respect, it's in some ways more similar to a functional language than an OO one. And sure enough, you can see that off disk, I load in Java-lang object, I set up methods corresponding to hash code and register natives, and then I run the CL init method. So this actually has a very cut down but working form of class bootstrapping as well. Okay, my time is pretty much up. So let's just see if this can run. Resources. Is it just main? Is it main 3? Ah, no, not quite. Oh well, I had a feeling that the last demo was the one that was going to break. Okay, well, let me just wrap up. So what's still to do? There's way more work to do on the class repo. I'm currently passing the repo around as a hidden parameter, but that has problems. The Java heap is the big question. I've tried a bunch of different things. I've tried using mutexes and get deadlocks. I've tried using cell. I'm contemplating the Rust GC module next, but that one is still a big open loop for me. Still, it's been lots of fun playing with it so far. Thanks to New Relic for sending me here this week. So I should also say that we're hiring. If you want to come and live in sunny Barcelona and work on cool stuff, I can't promise Rust programming, but I've got a bunch of jobs. So if you're interested or want to hear about what we actually do, come and talk to me or come to my talk tomorrow where I talk more about the New Relic-y side of things. And thank you very much.